Welcome back. This is Mr. Wakefield, and we're looking at now section 4.1 right at the beginning of chapter 4. And in particular, we're going to be looking at something called inverses, all right? Every function has an inverse. It's just a question of whether or not that inverse is itself a function as well, or is it not a function? And we talked about what the difference is between something that's a function and not a function back in chapter 2. Let me go ahead and remind you of what that is. Just a real simple function here where we just have four ordered pairs, all right? Not some big one where you got, like a graph or whatever, or a function formula. We're going to start real easy right now. If you just have four ordered pairs, the thing that makes this a function is that if all of the x's are different. Okay, we got four different ordered pairs. If all the x's are different, it's a function. All right. And then also just a reminder, since we're going to be talking a lot about domain and range today, remember the domain is all of the x's. So the domain would be 3, 2, 0, and 8. The range is all the y's. So the range would be 7, 9, 4, and 9. Or you don't need to say 9 twice right there. So that would be the domain and range. So here, let's take a look. So the domain here would be, let me write it down, 3, 2, 0, and 8. The range would be 7, 9, and 4. You don't need to say 9 twice. One for each one is fine. Okay, now, here's how the inverse works, you guys. The way the inverse works is that you take, I'm sorry, that fell off the screen there. There we go. So I got my domain and range there. But the way the inverse works is like this. You just simply take the x's and you change them to y's, and you take the y's and you change them to x's. In other words, you flip-flop all of the ordered pairs. 3, 7 becomes 7, 3, 2, 9 becomes 9, 2, and so on for the other 2 points as well. Because you flip-flop the x's and the y's, wouldn't it make sense for the domain, the brand new domain of the inverse, wouldn't it make sense that it would be the same as the range of the original function, since I'm flip-flopping the x's and the y's? So what was originally the y's is now the x's in the brand new inverse, all right? Inverse relation here. And because also because I flip-flop the x's and the y's, what was originally the x's, which is the original domain, is now the brand new y's, and so that will be the brand new range. All right, so let's say that one more time here. Whatever was the original domain is now the new range in the inverse. Whatever was the original range is now the domain in the inverse. All right, so the domain and range flip-flop as well, since domain and range has to do with x and y. That's not a surprise. Okay. Question though. Is the inverse here, this inverse relation, is this a function? It is not, okay, because we have a couple of ordered pairs that have the same x. Okay, so the original f up here was a function, all right? That's part of why I called it f, all right? But this brand new relation here is not a function because we have two x's that are the same. We'll get into more about that here in just a moment. But again, remember what we said about domain and range flip-flopping and x's and y's flip-flopping as you go from the original function to the inverse relation, all right? Okay, now, what I'm going to do right now, keeping that same concept in mind of the fact that x's and y's flip-flop, let's look at these first couple problems. If I know what the original graph looks like, and we have that obviously here in the first two problems, can I then come up with what the graph of the inverse looks like? All right, the inverse relation. All right, what is, and it might be a function, it might not be, but whatever the inverse is, can I come up with a graph for it? I can, and there's a way to do that. Again, remember that, and this is just going to be part of it. There's more to it than this, but we've got 3 points that are clearly plotted here, don't we? All right, those points are 0, -2 right here. This one is 2, 1, and this one is 4, 4. Remember, in the inverse, you flip-flop the x's and y's in every ordered pair that you have. All right, just like I did in this example right here. It's just that now, with the graph, I have an infinite amount of ordered pairs. All right, so there's a little bit more involved in as far as being able to graph it, but we can at least start off by taking the 3 points that we do clearly have and flip-flopping the x's and the y's. So this then right here would become -2, 0 on the inverse graph, which I'm going to put it in red so you can see the difference clearly. This one right here again was 2, 1, so if I flip-flop those numbers, I get 1, 2, and that point would be right there. And then this one, since it's 4, 4, what happens if I flip-flop 4, 4? It's still 4, 4, isn't it? And so on the inverse graph, we're going to have a point that's right on the same spot as that point was on the original graph. All right, now don't graph it yet because we just got 3 points. We don't know exactly what it's going to be. Here's something that you can do to be absolutely sure that your graph is correct. Now that I've got some points to kind of start with, here's what you do. You graph a dotted line, but it's a special kind of dotted line. It's a dotted line where it is a line that it has a y-intercept of 0, and it has a slope of 1. So which means that you rise 1 and you run 1. Okay, so I'm right here. Okay, this is not a part of either graph here. It's just a dotted line that's going to help us graph the inverse. It has a y-intercept of 0, and then you rise 1 and run 1. Okay, this is just to help me draw this dotted line right here that's going to help me graph the inverse. And I'll talk about how to do that here, but you got to have your dotted line first so that, okay, that can help you do that. Be very careful here, all right? As you see in a minute, it's very important to be as neat as you can here. Make sure your line is as straight as possible, all right? Again, that's really going to help you. Here's how it works, you guys. Once you put that dotted line on there, and let me turn it to the side here so that the dotted line is straight with the camera here, all right? Straight up and down with the camera. I know that's not the straightest line I've ever drawn, but so again, be as neat as you can here. But what happens is that anything that is on the right-hand side of the line here, and that would be from this point all the way down, wouldn't it? Okay, anything that's on the right-hand side of the line, I want you to imagine taking that side of the line and folding it over, just like my hand right here. Fold it over like this. Where would that piece of the line land if you folded it over from the right-hand side to the left-hand side? Wouldn't it land right here? Let me draw it. Okay. Doesn't it look like if I folded that part over right there, it would land right here? All right, so that's what you do. Anything that's on the right-hand side of the line, you fold it over, all right? The original graph is still where it's at, but in order to find the inverse, you fold it over, and then wherever it lands, that's where that piece of the inverse is. Okay, so anything that's on the right-hand side folds over to the left, but notice this little part of the arrow here, this little piece of the line right here in the original graph that's in pencil right here. All right, actually it's on the original printout, but it looks like pencil, as opposed to the red part, which is the inverse graph. This part right here, though, since that's on the left-hand side of the line, I'm now going to fold that over the dotted line again, and now it's going to be on the right-hand side, and that'll be part of the inverse as well. So if I fold that thing over, just that little piece right there, fold it over like this, wouldn't it look like this right here? Like that? See how it looks like that little piece right there, folded over on the other side? It's called a reflection, all right? It's like a mirror image of the other side of the dotted line. So that is how you do your inverse graph, is you take anything that's on the right, you fold it over, and then wherever it lands on the left, that's where that piece of the inverse graph goes. And then whatever was on the left of the dotted line, you fold that over, and then wherever it lands on the right, that's for that piece of the dotted line. Okay, so let's try that again here now on the next one. This next one's here a little bit more challenging, okay? It's a little bit more complex of a shape, but I'll help you kind of break it down here to see it a little bit better. Let's start off here, though, by putting our dotted line on there. Okay, and you can go like this here. Again, it is what? It is y-intercept of 0, slope of 1. So we rise 1 and run 1. Rise 1 and run 1 from here. Rise 1, run 1. And then we draw that dotted line like this. Okay. So let me do that. Like that. The other thing that'll help us, like it did in the last problem, is take all the clearly plotted points right here. We've got a total of 5 of them here. And let's flip-flop their x's and y's. It'll help us locate the inverse graph as well. All right, just relying on folding the page over is kind of tough, especially in a complex-looking graph like this. So let's do that as well with the points. This right here is negative 2, 0. So if I flip-flop those, the inverse graph will now have 0, negative 2. Let's go to the next one. This one right here originally was negative 1, 3. So on the new graph, it's now going to be 3, negative 1, like that. This point right here is 0, 0. So if you flip-flop that, obviously that's still going to be 0, 0, right? So that point will not only be on the original graph, but also on the inverse graph. In fact, any point where the x's and y's are the same will always be on both graphs, both the inverse graph and the original graph. In fact, the graphs will intersect each other there. As you can see, 4, 4 intersected there. Not a surprise, because since those points are supposed to be on both graphs where the x and y are the same, they should intersect each other, all right, at that point. Let's keep going here. What else? So how about this point right here? This point is 2, negative 3. 2, negative 3. So if I flip that, I now have negative 3, 2. That would be way over here. All right, and then this last one right here, that's 3, 1. So if I flip-flop that guy, it's now going to be 1, 3. Okay, so got a lot of stuff going on here, all right? Let's start out with the easier parts here. As you can see here, let me flip this around. Okay. Zoom in a little bit. There we go. If you just look at this piece right here, we're going to take one piece at a time. Remember, you're supposed to take anything that's on the right-hand side of the line and flip it over to the left, fold it over to the left. Okay, this right here is on the right-hand side of the line, but what's connected to it up here is not. So we're just going to look at this only. All right, this also over here is on the right-hand side of the line, but because the two pieces that are on the right-hand side of the line are separate from each other, they're disconnected from each other, let's do one at a time. Let's start out with this little piece, and then we'll do the bigger piece. Okay, now, if I take that piece right there and I fold it over, again, imagine that little arrow there folding over, wouldn't it end up right here? Okay. You see that right there? All right. I made it a little bit longer there than I should have there. But that's okay, because the arrow is implying that it's going to go longer anyways. It'd be like if you went like this right here. Okay. So it's okay to make it a little bit longer when the arrow is there, because the arrow implies that it goes in that direction anyway. So folding this over would put that right here. Okay. Same thing with this one over here. All right. If you fold that one over, you know, I'll get back to that in a minute. I don't want to move too fast here. Let's just do one piece at a time here. This part right here is on the left of the line, from here to here. That piece right there. What happens if I fold that over? Well, that's kind of tough to see when you got all this other stuff going on at the same time. So what I'm going to do is I'm going to look at that separately right here. Let's just look at that one piece only. See how I got rid of the rest of the graph, got it out of there. Let's just look at that one piece right now, isolated here. If I fold that thing over to the right-hand side of the line, what's going to happen? It's going to look like a heart shape, like this, right? Okay, so let's do that same thing here. All right, if I fold just this piece right here, it's going to be a heart shape. But now, this is my fault, by the way, you guys. I put the grid lines here are a little bit off, where the X marks are a little bit wider apart than the Y part. So it's going to be a little bit off. That's okay. That's my fault. All right. So if it doesn't look perfectly the same on both sides, all right, that's okay. In fact, the heart that I'm about ready to draw here, the right-hand side of the heart is going to look a little bit more narrow and long than this part does. But again, that's because my grid lines are a little bit off. But notice here that we should get something like this right here. Okay. Okay, so you can see the heart is a little bit off there where it's longer and more narrow on this side. But again, that's just because the grid lines are a little bit off, all right, on the printout. It's kind of tough to make perfect grid lines, all right? So sorry about that if that is a little bit confusing. But again, remember the idea is to fold it over, all right, and make it look the same on the other side, like as if you folded it over. It's just that it's a little bit more narrow there because of the grid lines. Now let's take a look at this part right here, the original penciled in part here from this point all the way up to here. All right. Again, there's so much stuff going on here. So let's just take that one little piece and let's put it off to the side here and get rid of everything else. It would then look like this, wouldn't it? And so if I took that piece right there, you guys, and I folded it over, what would it look like? It would look like this right here. Okay. Like that. Okay. So that same thing is going to happen here. It might be a little bit skewed because of my grid lines again, but you'll see here that the same idea is going to happen. Again, notice I'm using my points here. That way you know exactly where it crosses through, all right, but it's this shape right here. Notice also that, remember, the original graph and the red graph are always going to intersect each other right on the dotted line, okay? So wherever the graph, wherever the original graph hits the dotted line, the inverse graph will always hit it at that same spot too. So I knew that it was going to hit right there, and I knew it was going to go through these points that I already plotted, and so that helped me draw this shape right here, this red shape. All right, so use those points to help you. And then lastly here, I have one more part of the graph here. It's just this little arrow here. If I take that and I fold it over to the other side, it is going to be this right here, isn't it? Like that. So not an easy graph to do right there, but if you look at each piece separately one at a time like this, it makes it a lot easier to see how it folds over. All right, and then like I said, graphing the points where you flip-flop the X and Y certainly helps you as well. Okay, so that is how you graph an inverse. We'll be seeing more graphing of inverses here coming up on the back side of the sheet. Before I do that, though, I like to go back to this scratch piece of paper once again. You don't have to write this stuff down. That's why I put it on a piece of scratch paper partly. But it just helps you understand some of these things that we're doing a little bit better. Okay, now, again, we already agreed that the if the original function has y. First of all, in order for the original function to actually be a function, all the x's have to be different. We've known that since chapter 2. But if some of the y's are the same, that doesn't affect whether or not the original thing is a function, but it does cause the inverse to not be a function, because when the y's go into the inverse, they become x's, don't they? and you can't have x's that are the same. So if the original problem had y's that are the same, that means that the inverse will then have x's that are the same, and you can't have that. Now, it could still be an inverse. It's just that the inverse is not defined as a function. That's all. Okay? So what would I have to do in order to have a function whose inverse also is a function? Okay, let me just tweak this a little bit right now. Okay, suppose I changed this 9 right here to a 6 so that all the y's will be different. Okay, if I did that, then the range would then become what? It would have that 6 in there also. Let me just throw that in there. It doesn't matter what order you put the numbers in as long as you got them all in there. 7, 9, 4, 6. That would then make this also down here. The domain down here, it would make this 7, 9, 4, 6. And the original 6 here would then become a 6 right here. Let me change that 9 to a 6 there as well. Okay, but I want you to notice something here. Now all of the x's are different in the inverse because all of the y's were different in the original graph. So what do we need in order for the inverse to be a function? Not only do all the x's have to be different in order for it to the original one to be a function in the first place, but all the y's need to be different also in order for the inverse to be a function also. So in order for the inverse to be a function, both the x's and y's have to be different. Okay, they have a name for that. When all the x's are different and all the y's are different, that is called a one-to-one function. All right. In other words, every x matches up with one and only one y, and every y matches up with one and only one x. It's a one-to-one relationship that they call it. Okay. Now, as it turns out, because the x's and y's change roles as you go from the function to the inverse, you guys already know that in order for a graph to represent a function, it has to pass the vertical line test. We learned that in Chapter 2, Section 2.3, if you want to review that. Okay, you can see here that this graph right here, every single vertical line in the world goes through the graph exactly one time here. Okay, never more than that. So as long as no vertical line ever hits the graph more than once, it's going to be a function. And you don't need to graph the inverse here, all right? They didn't ask for that. But in order to figure out if the inverse, whatever it may be, in order to figure out if it too is a function, which is the same thing as saying that the original function is one-to-one. If the original function is one-to-one, then the inverse will be a function also. Okay? And you can see here, it talks about that. It says that if the inverse is a function, that means that the function passes the horizontal line test. I'll get into that in a minute. All right, and that means that it's a one-to-one function. So one-to-one is synonymous with the fact that the inverse is a function. All right. So in order to be one-to-one, not only does the graph have to pass the vertical line test, it also has to pass the horizontal line test. Does any horizontal line go through this graph more than once? Yeah, a whole bunch of them do, right? See how all these horizontal lines hit the graph twice as it goes through the parabola here? So because of that, yes, the original function is actually a function because it passes the vertical line test. But because it does not pass the horizontal line test, it is not, the inverse is not going to be a function. If I were to graph the inverse right now, you guys, it would actually look something like this. It would look like a sideways, but you don't have to do it. Don't get me wrong. You don't have to graph it. I'm just saying, if you were to graph the inverse by using the dotted line and all that stuff that we just talked about, you would get something like this. And that, as you can see, doesn't pass the vertical line test. So in order for the inverse to pass the vertical line test, you don't need to graph it. You just need to take the original graph and see if it passes the horizontal line test. All right, so let's write this down. Since the original function f does not pass the horizontal line test. Okay. The inverse is not a function. I know they didn't ask that. You were just wondering if it was one-to-one. But remember, those things are synonymous. If a function has an inverse that's also a function, that means it's one-to-one. But since this inverse is not a function, okay, this means what? That means that f is not one-to-one. One-to-one. Okay. All right. So, in order to figure out if the inverse is a function, you figure out theoretically whether or not the inverse passes the vertical line test. But you don't even need to graph it to find that out, because again, in order to find out if the inverse passes the vertical line test, you just have to figure out if the original graph passes the horizontal line test. How about this graph right here? Does this pass both the vertical and the horizontal line test? All right. It already says that it's a function, so you know already that it passes the vertical line test. They wouldn't call it a function if it didn't. So you just theoretically really need to figure out if it passes the horizontal line test. I mentioned the vertical line test over here just to remind you again that all functions do pass that vertical line test. But you don't need to test that out because they're already telling you that it's a function. But is the inverse a function? Well, if it passes the horizontal line test, and does it? Does every single horizontal line pass through the graph once? It sure does. You can see that there are no horizontal lines ever going to cross through this diagonal line right here more than once. Okay, so since f passes the horizontal line test, okay, its inverse is a function, and the original function f is 1-to-1. Okay? So that's how to figure out, at least by using the graph, that's how you figure out whether or not a function, the original function, is 1-to-1. Okay? Okay, flipping over to the back side of the 4.1 worksheet now, you can see it gives us 5 problems here. It gives us 5 functions. And it asks multiple questions here. It says, for each of the following functions, if it is not 1-to-1, say so, and then move on to the next problem. So if it's not 1-to-1, then that's all you got to do is just say that. One of these 5 problems is like that. We'll see which one it is here in a little bit. It's not the first one. If it is 1-to-1, which as you'll see in just a moment here is 1-to-1, the first one here, we're going to do the following things. We're going to write an equation for the inverse function, and we call it f with the -1. I know that looks like an exponent, but it's not. F -1 means the inverse function of f. All right, we'll talk about how to figure that out. And then we'll graph them, but not in that necessarily in that order, but we will graph both of the f and the inverse function for f on the same grid, on the same axes. That's the same thing as putting it on the same grid here. And then give the domain and range of both of those things. Okay, so the best way to find out if it's 1-to-1, obviously you want to find that out first, because if it's not, you can stop, and you should stop, is to actually graph it. And since this is in the mx plus b, the y equal to mx plus b form already, we realize then that this is a line, okay? This is 4/1 times x minus 5. All right. Back in chapter 2, we talked about that. Just to give you a little visual right now. Let me show you that. Okay, so again, when you've got y equal to a constant times x minus a constant, or it could even be plus, it's still going to be a line either way. We know that the slope is that thing that's being multiplied by x. All right, and then b is whatever's being added to that. So plus -2 is the same thing as what we got here, and so that would be the b number, which is the y-intercept. So that means that I'm going to put it up here because it's going to be we need the room here. The slope is what? The slope is 4/1, so that means we're going to rise. Sorry about that. There it is. The slope is 4/1. That means we're going to rise 4 and then run 1. The y-intercept is -5. -5. Okay, and so let's go and graph that now. If the y-intercept is -5, we always start out with that before we do the slope. And there it is right there. And then rise 4 and run 1 takes me all the way up to here. Okay, so our original graph is just to draw a line through those 2 points, since we know that it's a line when it's in the mx plus b form. Okay, please be, again, as straight as you can with this line, okay, because when you do the inverse graphs combined with the regular graph, all right, it's very important when you do the reflections and the dotted line and all that to be as neat as you can so it doesn't get confusing for yourself mainly. All right, don't want to see that happen. So just use a straight edge right here. The pen will be fine. And there you go. All right, now is that 1-to-1? What does it mean to be 1-to-1? It means that it not only passes the vertical line test, which we didn't already know that it was because it didn't say it was a function. Oh, you know what it does? I apologize. It does. It says for each of the following functions. So we know it already passes the vertical line test since they told us it was a function, but does it pass a horizontal line test? You can see that it does here. All right, we're going to have a lot of other stuff on this graph, so please do not put those horizontal lines through there. Just imagine them in your mind going through this graph, and none of them hit the graph more than one time. So, step 1 here. Okay, graph passes the horizontal line test, doesn't it? Since it does, okay, it is 1-to-1. What do I mean by it? I meant the function. Function is 1-to-1. We call it y, but since the graph passes the vertical line test, we know it's a function. But because it passes the horizontal line test as well, we say that it's 1-to-1. Okay. All right. What's step 2? Step 2 says that if it is 1-to-1, then what do? We write an equation for the inverse function, and let me show you how to do that right now. And then we can focus on doing the graph of the inverse at that point. But because it's 1-to-1, the inverse function will indeed be a function. Let's find out what that is. The way you do that is you take your original graph, and if this is f of x right here instead of y, change it to y. You want it to be y instead of f of x. All right, see here in problem number 7, for example, since it's f of x, change that to y. But since this already is y, then that's what we want. We want to have x and y in the problem. We don't want to have x and f of x in the problem when we do this step. All right, so what you do is, let me just bring it down here to start us off. All right. What you do first is you interchange the x and the y. Wherever you see the y, change it to an x. Wherever you see the x, change it to a y. All right, remember, this makes sense because when you have inverses, the x's and y's change places, don't they? And so it makes sense that they would in the equation as well, not just with your points on your graph, but also in the equation too. All right, once you do that now, as we learned back in when we reviewed in the prerequisite review packet, very last worksheet of that packet, we learned that if you've got more than one letter in a problem, okay, and you need to solve for one of those letters, all right, we talked about how to do that, okay. in this problem, we have what? We have we need to get the y by itself. And let me make that absolutely clear. After you interchange the x and the y, you then need to get the new y, which is not the same as the old y, because the new y is the same as the old x. Okay? So there's the old y, but then the old x is what becomes the new y. All right? Okay, so we need to get the y by itself then. How do we do that? Well, this is a linear equation. Both sides are polynomials. We just have x and y. There's no x squared or y squared. So it's just like these problems here back in the review packet at the beginning that we talked about at the beginning of the semester, where assuming there's no parentheses to clear out first, all right, we identify our terms that have the variable in it you're trying to get by itself, and then the ones that don't are separate. So that's why I had red and green. It's the same thing here. We want to get the y by itself, so that'll be the red one, and then the ones that don't have the y in it are the green ones. And so the idea that we learned before is that we get the green ones on one side and the red ones on the other side. Same thing here. All right, and the way we do that is by adding or subtracting the terms from one side to the other. So this would be what here? This would be x plus 5. 5's cancel right there. You get 4y. And then once you get the red term by itself with the variable in it that you're trying to actually get by itself, then you divide out, and that gets the variable completely by itself. Now that y is by itself, here's the thing. The new y that we have now, that is not f of x, okay? That is f inverse of x. Again, it is different from the old y. The old y, the original y, that's f of x. But the new y, which was the old x, that is f inverse of x. That's the inverse function, okay? So the inverse function is equal to x plus 5 over 4. So whatever your new y is equal to, okay, that's your f inverse. All right, and so since it's equal to this fraction, that's what the inverse function is. It's equal to that fraction. Okay, now, once you establish what your inverse function is, the formula that is, okay, x plus 5 over 4, what you do is you have one of two choices here. You could either use that formula to graph it, and I could split this apart here like I do when I do mx plus b, and I could say 1/4 x plus 5/4. You could graph that way, or you also have the option of doing what we learned on the front side of this worksheet, where you just take the original graph and do the dotted line thing, and then you reflect it over that dotted line. I'm going to go ahead and do it that way. But you could do it the other way with the formula as well, because we know how to graph a line, obviously. So let me do that. Okay. So there's my dotted line right there. And again, what do? As we did on the front side of the worksheet, you take the points that you already know, and you could plot more points than this if you want by just simply plugging in numbers into the original function here and get more points. Sometimes more points makes it easier to graph when you do the reflection over the dotted line. But let's take the 2 points we already have. This one is 0, -5. So if I flip that around, it's -5, 0. Okay. This one is 1, -1. So now if I flip that around, that's going to be -1, 1 now. Okay. Another thing that we do know is that whenever the graph crosses the dotted line, the inverse graph also has a point right there, because it always intersects at the dotted line. So we now have 3 points right here. But in order to be sure that we're doing it correctly, again, turn your thing to the side here so that the dotted line is going straight up and down, and then just look at it and look at what part on the right-hand side of the line, what would happen if that folded over to the other side? Okay, what would it look like? It would look like this right here. Okay, I made it a little bit longer than this, but again, because there's an arrow, that's okay. All right. Because we know that arrow is going to keep on going in that direction anyway, and then it would end up being just as long as the red one is. Okay, so it's okay to make it a little bit longer when it has the arrow there. And then what do we do after we take the part that's on the right-hand side of the original graph and reflect it over? We then take the part that's originally on the left side of the dotted line and we fold that over so that wherever it lands on the other side, that is that part of the inverse graph. All right, and so it would end up being right about here, wouldn't it? Okay, and so that is the inverse graph. All right. So we have now done what? We've now found the f inverse of x formula, like they asked us to write an equation. We did that here. We graphed both f and f inverse. Okay, the original graph here is f. You don't have to label this, all right? It's already clear what it is. I'm just being extra clear here. This one was f because it's the original graph. This one is f inverse. Okay. And so the last thing we need to do is it says give the domain and range of both f and f inverse. Okay, I'm going to say D with a little f underneath it, R with a little f underneath it. That is the domain and range of f, not f inverse, but just f. What is that? Well, anytime you have a line, unless it's horizontal or vertical, it is going to be, it's going to have a domain and range that are both negative infinity to infinity. Okay, both of them will be negative infinity to infinity. All right. Remember we talked about how to figure out domain and range by looking at the graph. If you have arrows that go in a diagonal fashion like this, that means it goes forever to the left and forever up. Okay, another diagonal one here. This one is forever to the right and forever up. Well, this one, it goes forever in 4 different directions, all 4 directions. Okay, this one goes forever up and forever to the right. This one goes forever down and forever to the left. Okay, that's all 4 directions. And when it goes forever in all 4 of those directions, left, right, up, and down, then that means that everything is infinity or negative infinity. Okay, remember domain is the leftmost point. So if it goes forever to the left, it's negative infinity. It ends at the rightmost point, but if it goes forever to the right here, then that means that it goes to positive infinity. Okay, when it goes forever down, that means that the range starts at negative infinity. And when it goes forever up, that means it ends at positive infinity. But just to make this long story short here, you guys, if you have a line, any line at all, doesn't matter what it is, as long as it's a diagonal line and it's not horizontal or vertical, the domain and range will always be the whole thing from negative infinity to infinity. Okay, the entire number line if you were to graph it on a number line. Okay. So, what about the domain of f inverse and the range of f inverse? Okay. The domain and the range need to match up in the sense that the domain of the original graph, as we said on the front side of the worksheet, that has to match up with the range of the inverse. Okay, if it doesn't on your graph, then you need to make an adjustment on both your formula and your graph because these need to be the same. That absolutely needs to be true. Okay, the graph here seems to indicate, because it's a line that's not horizontal or vertical, the range will be this. Okay, so everything's working out fine. All right. If the graph does not match up with the domain and range of the inverse, then you need to do something. We'll talk about that here when that becomes an issue. It's not an issue in this problem, but this domain right here of the inverse has to match the range of the original. So again, domain matches the range of the inverse. The range of the original has to match the domain of the inverse. Okay, and so the graph indicates that it's consistent with these 2 answers right here for the domain and range because all lines other than horizontal and vertical have that domain and range. So everything is as it's expected to be. All right. But as we'll see later, sometimes you'll get a domain and range for the inverse that does not match up with the graph that you may have graphed before that on the previous step. When that happens, we'll make an adjustment. I'll talk about how to do that. Okay, in number 2 right here, if you go back to chapter 2, you'll find out, you'll be reminded that when you have, okay, let me give you a good example here. If you've got f of x or y, same thing, okay? If you got f of x or y that's equal to something that has x squared in it, okay, then it's going to be based off of the basic graph from the previous section 2.6, which tells us that that basic graph for x squared is a parabola. And so negative x squared plus 2 also fits into that category right there. All right, if you've got x squared multiplied by a constant and then you add a constant to that, okay, that fits in the groundwork of what we talked about in this section, where it should be just like x squared itself. It should be just like this right here. It's just that you have to go through the process of graphing it, all right, in order to figure out exactly where that parabola is, but it will be a parabola nonetheless. Now, here's the thing. You don't need to graph it this time. And the reason why is because we know that all parabolas, no matter where they are, whether the parabola is down here, parabola is over here, it's not going to pass the horizontal line test, is it? Okay, let's write that down. Okay, we know from 2.7 that this function is a parabola, okay, because it stems off of the x squared basic graph that we learned there. All right, and since parabolas never pass the horizontal line test, okay, since they never pass it, okay, this function is not one-to-one. And as we said at the beginning, okay, if it's not one-to-one, just say so and move on to the next problem. Not one-to-one. And that's it. We can go right on to the next problem.